Imagine a telescope more powerful than any on Earth, not just because of its size, but because of its location. Picture a vast metal net, strung across a crater on the far side of the moon, silently listening for whispers from the universe's earliest moments. This isn't science fiction. This is NASA's new plan to save the future of astronomy, and perhaps our understanding of the universe itself. But why go to such extremes? Why spend a staggering $2.6 billion to build a radio telescope where no human has ever set foot? The answer may surprise you, and it involves not just science but the unseen consequences of our modern, connected world. You're about to discover how the chaos of Earth's satellite explosion, the promise of cosmic discovery, and the battle for the moon's quiet side may forever change the way we look at the stars and ourselves. Let's dive in. First, let's rewind for a moment. Radio astronomy began almost by accident. In the early 1930s, a young engineer named Carl Jansky was investigating static that disrupted wireless transmissions, a real inconvenience for Bell Labs. What he stumbled upon, though, was nothing less than cosmic radio waves emanating from the Milky Way. Suddenly, the universe had a new voice, and humanity gained a new way to listen. Fast forward to 1937. Grote Reber, a radio enthusiast from Illinois, was so inspired by Jansky's discovery that he built the first purpose-built radio dish in his backyard. What started as tinkering exploded into an entire field. Over the next several decades, giants like the Arecibo Observatory in Puerto Rico and China's FAST telescope set the pace, each vying to peer deeper into the cosmos. Why all this effort? Because radio telescopes can detect things that no optical telescope ever could: signals from pulsars, whispers from exoplanets, and, most importantly, the faint static of the universe's infancy, the so-called cosmic dark ages. But here's the catch. Radio waves are everywhere, and as our planet becomes saturated with more and more human-made signals, cell towers, Wi-Fi, and most recently swarms of satellites, Earth's radio noise floor keeps rising. Even the world's most remote radio observatories, nestled in deserts or shielded valleys, can't escape. It's like trying to hear a pin drop in a rock concert. According to Federico Di Bruno of the Square Kilometre Array Observatory, it would mean that we are artificially closing windows to observe our universe if radio astronomy on Earth becomes impossible due to interference. That's not just an inconvenience, that's a crisis for science. How bad is it really? Consider this. The far side of the moon offers a radio environment up to 1,000 times quieter than the most isolated location on Earth. That means for every faint cosmic whisper an Earth-based array might miss, the moon's dark side could catch it loud and clear. So what's causing all this interference? The answer is flying above our heads. Satellites. Thousands, soon tens of thousands of satellites from commercial operators like Starlink, OneWeb, and Amazon's Project Kuiper now crowd low Earth orbit. While this space race is fueling a new era of connectivity and opportunity, it's also drowning the sky in radio frequency leakage. Earth-based radio observatories are increasingly reporting ghostly streaks and flashes swamping their sensitive feeds, even in supposedly protected frequency bands. And it isn't just the satellites. Every year, our appetite for wireless technology grows. Towns and cities are lit up with Wi-Fi hotspots and 5G masts, emitting energy across the electromagnetic spectrum. For radio astronomers, who live to detect signals fainter than the faintest star, it's a nightmare. This is where NASA's audacious idea comes in. If we can't escape the noise on Earth, why not take the search for cosmic secrets somewhere entirely shielded, somewhere like the moon's far side? Enter the Lunar Crater Radio Telescope, or LCRT. If you've never heard of it before, don't worry. It still sounds almost like science fiction. The concept is simple but monumental. Lower a wire mesh, over 350 meters across, into a crater on the moon's far side. Suspend it by robotic cables, and let it listen. No city lights, no cell towers, no satellites in direct line of sight, just silence. Dr. Joseph Lazio of the Naval Research Laboratory puts it starkly. The lunar far side is the quietest place in the inner solar system for radio astronomy. Can you imagine scientists finally hearing the universe's most ancient stories, unfiltered, unspoiled? Now here's what's truly game-changing. The LCRT isn't just another telescope. It can tune into ultra-long radio wavelengths, over 10 meters long, that Earth's own ionosphere blocks. These wavelengths are vital for peering back before the first stars. They're the keys to unlocking the universe's cosmic dark ages, a period when nothing shone but the glimmer of primordial hydrogen. Dr. Gaurangi Gupta, a lead scientist on the project, argues that observations of the dark ages have the potential to revolutionize physics and cosmology by improving our understanding of fundamental particle physics, dark matter, dark energy, and cosmic inflation. In short, the LCRT could help answer the deepest questions in science. Where did it all come from? Why does the universe look the way it does? What rules govern reality itself? But before we get swept away by possibilities, let's pause and ask, is this even possible? Can we really build a world-class observatory, remotely, robotically, on one of the most hostile landscapes in the solar system? Let's take a look at what the blueprint for the LCRT actually involves. The preferred site is a lunar impact crater, chosen for its natural bowl shape, perfect for stringing that vast mesh reflector. It's not publicly revealed yet, but NASA's team has their eyes on a site in the Moon's northern hemisphere. The telescope's main catching surface, a wire mesh stretched by robotic landers across the crater's diameter, would be larger than the legendary Arecibo dish and nearly rival China's FAST. But unlike on Earth, there's no air, no weather, and thankfully, no noisy neighbors. How would NASA and its partners pull this off? The current plan is for a robotic construction crew, likely launched in stages, to assemble the telescope wire by wire, using advanced robotics and perhaps future lunar rovers. The project has now progressed past conceptual stages and is testing prototypes in California. It has already passed several rounds of review by NASA's Institute for Advanced Concepts. Still, just because you can build something doesn't mean you should, or that the world will pay for it. The LCRT comes with a jaw-dropping price tag, $2.6 billion at last estimate. For context, that's almost as much as the James Webb Space Telescope. And NASA, with its ever-tightening budget, is struggling to find room. As Gaurangi Gupta notes, funding is the most significant obstacle right now. Every year, new priorities arise. Crewed Artemis missions, lunar gateway stations, Mars rovers. If the LCRT makes it to the next funding round, it could move toward becoming a fully fledged mission by the next decade. But nothing is certain. And money isn't the only challenge. Lunar dust could gum up delicate machinery. Extreme lunar cold, down to -170 C at night, and searing heat by day threaten electronics. The site must be chosen for both stability and accessibility, yet secrecy shrouds even its location, for now. Then there's the challenge of operating and maintaining a telescope nearly 400,000 kilometers away, with a nearly half-second communications delay, assuming, of course, that nothing on Earth or space disrupts the delicate radio silence required. On top of all this, there's a sense of urgency creeping in. Each new satellite launch pushes Earth-based radio observatories closer to the edge. Some in the astronomical community worry we may see, within a decade, a point of no return, a world where the faintest traces of the early universe are permanently drowned by man-made noise. Dr. Philip Erickson of MIT's Haystack Observatory stresses, lunar-based observatories are essential for studying ultra-long wavelengths blocked by Earth's ionosphere. In other words, the window for fundamental discoveries is closing, and the Moon may be our last best hope. But what about smaller, more incremental steps? NASA isn't betting everything on the LCRT right away. In 2024, the agency landed its first experimental radio instrument, ROLSIS-1, on the Moon's near side. The results? Disappointing. Positioned facing Earth, it mostly picked up the usual wall of radio chatter. Later this year, another, more ambitious test will attempt to set a working radio telescope on the far side itself. The hope is that these pathfinders will prove both the value and viability of the LCRT. And yet, at every turn, there are whispers of doubt. Is the scientific payoff really worth the multi-billion-dollar gamble? Will the fight for lunar resources, land, and radio silence unleash new geopolitical rivalries? Can robots build and maintain what humans can't yet reach? And if we succeed, what will we find, listening in the utter silence of the Moon's far side? The stakes have never been higher. On one side, a future where cosmic discovery continues, breakthroughs in fundamental physics become possible, and the Moon itself becomes humanity's next great observatory. On the other, a losing fight against Earth's ever-rising noise, a closing window on the universe's deepest secrets, and the end of an era for scientific listening. The question is, are we willing and able to pay the price? As nations, tech giants, and scientists compete for a foothold on the Moon, the true battle for cosmic knowledge is just beginning. What happens if the LCRT fails, or if it succeeds? And what unforeseen consequences might this unprecedented leap bring to both science and global politics? Stay tuned. because the next chapter in the story of the Lunar Crater Radio Telescope may change not just how we do astronomy, but what it means to be human, always seeking, always listening, and forever reaching beyond our noisy world. So, what could the future really look like if NASA succeeds, or fails, in building the Lunar Crater Radio Telescope, the LCRT? Let's dive into the consequences, the unpredictable twists, and the real-world impact of this lunar gamble. Imagine this. The year is 2035. After years of overcoming technical setbacks and budget debates on Earth, the first images from the LCRT begin to trickle in. The scientific community holds its collective breath as data from the silent, radio-shielded depths of the moon's far side arrives for the first time. It's the kind of moment that could redefine how we see the universe, or remind us of just how vulnerable our scientific ambitions are in the face of Earth's growing technological noise. But what exactly is at stake? Let's start with the scientific ramifications. If the LCRT succeeds, astronomers will get their first unobstructed glimpse into the universe's most mysterious epoch, the so-called cosmic dark ages. This is not science fiction. Before the first stars and galaxies flickered on, the universe was shrouded in hydrogen, dark matter, and photons, an era completely hidden from traditional telescopes. The only clues from that time are encoded in ultra-long radio waves, the cosmic whispers that terrestrial telescopes simply cannot hear. According to Dr. Joseph Lazio of the Naval Research Laboratory, the lunar far side is the quietest place in the inner solar system for radio astronomy. That's not just poetic, it's literal. The moon's bulk physically blocks Earth's torrent of radio transmissions, offering a pristine, almost sacred environment for listening to these faint signals from the dawn of time. If we unlock those signals, as NASA's Gaurangi Gupta puts it, observations of the dark ages have the potential to revolutionize physics and cosmology by improving our understanding of fundamental particle physics, dark matter, dark energy, and cosmic inflation. This isn't just about pretty cosmic pictures. It's about rewriting the textbooks on what the universe is, how it began, and possibly even why it exists in the first place. But let's not underestimate the risks. What if the LCRT stumbles? The engineering challenges are daunting. Picture a wire mesh the size of several football fields, delicately suspended within a lunar crater. Lunar dust is notorious. It coats everything, gets into every joint, and can degrade sensitive equipment. Extreme temperature swings between lunar day and night stress even the toughest materials. And then there's the staggering $2.6 billion price tag, which could swell if unforeseen obstacles arise. If the LCRT fails, not only will Earth lose a vital window for radio astronomy, but will also hand a severe blow to lunar exploration itself, a setback that could ripple across generations of science. Zooming out, there's also a geopolitical edge to this race. As the moon becomes a hot destination for national and commercial ambitions, the far side's relative quietness could transform it into the most important patch of real estate in the solar system for science. Imagine a scenario where multiple countries vie for access, or even claim exclusive rights, over the best lunar craters. If NASA builds the first successful far-side radio observatory, it could trigger both collaboration and competition, potentially leading to a network of lunar observatories or, as some warn, a new kind of space race. Such competition could have profound consequences. Will the far side of the moon become a haven for peaceful scientific discovery, or a battleground of conflicting interests? Will regulations be established now, before the land rush begins, or will humanity repeat the mistakes of Earth by letting short-term ambition override shared stewardship? Yet, in every challenge lies opportunity. The robotics, materials science, and construction techniques developed for the LCRT could spark advances that go far beyond astronomy. To build and maintain a telescope in the harsh lunar environment, NASA and its partners will need to develop autonomous robots capable of delicate assembly and self-repair, technologies that could one day build lunar habitats, mine lunar resources, or even prepare the way for Mars missions. Think of the LCRT as a test bed for humanity's future in space. If we can learn to operate complex machinery semi-autonomously on the moon, it's not a stretch to imagine swarms of robots laying the foundations for the first permanent lunar outposts or harvesting lunar ice to provide water and fuel. The LCRT could be remembered not just as a telescope, but as the first inkling of a self-sustaining lunar economy, a moonshot that pays off in ways we can hardly predict. There's another, subtler shift that could ripple back to Earth. By highlighting the fragility of our observational windows on the universe, the LCRT project may spur us to rethink our relationship with technology. The relentless expansion of satellite networks, a marvel of connectivity, comes at a hidden cost to fundamental science. It's a reminder that our actions, however well-intentioned, can obscure the very signals that helped spark our curiosity about the cosmos in the first place. Federico Di Bruno, an astronomer with the Square Kilometre Array Observatory, warns that if radio astronomy from Earth becomes impossible, we are artificially closing windows to observe our universe. It's a call to action, urging us to balance technological progress with the need to preserve humanity's capacity for discovery. The moon, paradoxically, may become both sanctuary and symbol, a final refuge for truths that Earth's noise drowns out. So, what does all this mean for you, our viewer? First, it's a rare opportunity to witness the making of history. The LCRT is more than a NASA engineering challenge. It's an experiment in international cooperation, technological innovation, and cosmic curiosity. As debates about lunar governance, satellite regulation, and space exploration heat up, your voice, your awareness, matters. If you care about science, this is your moment to advocate for the protection of humanity's last quiet places. Stay informed about space policy and support leaders and organizations working to balance progress with preservation. Follow the unfolding story of the LCRT and ask the tough questions. Who gets to decide what happens on the lunar far side? What values do we want to export beyond Earth, the lessons of stewardship or the excesses of exploitation? Even beyond policy, the LCRT story offers a powerful lesson about the interconnectedness of human ingenuity. The same technologies developed for lunar construction might one day help address tough problems here at home, from building robust renewable energy systems to managing complex autonomous infrastructure. Every breakthrough on the moon could pay dividends on Earth. On a personal level, it's a reminder that the universe is still full of unsolved mysteries. The cosmic dark ages remain uncharted, a realm older than the first star, holding secrets about our origins. You don't have to be a scientist to feel awe at the prospect of peering that far back in time. Supporting science, advocating for responsible exploration, and fueling curiosity in yourself and others. These are the ways we all participate in humanity's grand adventure. Now, as we draw this journey to a close, it's time to circle back to that burning question from the start. Can the LCRT really be built? Will it work? And what will it mean for science and the world if it does or doesn't? The answer is, we're on the threshold. All the pieces, technology, ambition, even funding potential, are coming together as never before. The risks are real, but so are the rewards. If the LCRT rises from the lunar surface, it could unleash a new era of discovery, open a permanent window to the oldest epochs of the universe, and pioneer methods that push humanity further into the solar system. If it fails, it will serve as a profound warning that as we race forward with technology, we must never lose sight of the delicate balance between progress and preservation. And now, as promised, here's a secret fact. The chosen lunar crater for the LCRT already exists. It's been quietly earmarked in the moon's northern hemisphere, but its exact location is kept confidential to prevent political competition and preserve its scientific integrity. The race is not just about science, but about who gets there first and how wisely they use the privilege. The story of the Lunar Crater Radio Telescope is still being written, but the next chapter will depend on all of us, on our choices, our curiosity, and our resolve to protect the precious windows into the cosmos. If this journey into the moon's mysteries inspired you, don't forget to hit like, subscribe, and share your thoughts in the comments. What questions